Hey, so we talked about function templates and now we want to introduce class or struct templates. Class templates are generic classes with placeholder types that can be substituted for actual types, allowing the class to be utilized with different types. So basically what we do is we define a generic class template and we allow the user, or in other words the programmer, to specify what type the class must utilize. Placeholder types are used for members, return types, or formal parameters. It's very flexible in that way. You can do a lot with that type parameter. Remember that we cannot overload classes in the same way that we can overload functions. But if you have two classes with the same name, or in other words the same identifier in the same scope, or in the same namespace, you are not going to overload that class. You are simply going to get a conflict. So again, you want to avoid that. Now, a class is by itself a blueprint for the actual objects that you eventually want to instantiate or construct. So in this way, with classes or templates, we can generalize those classes even further, or in other words create even more abstract classes. Here's a quick example of the class template prefix, and that is going to indicate to the compiler that the following class is a template. As with the function template, you are going to use the template keyword, the angle bracket, type name or class, and then you specify a type parameter. In this example, we will use t for the type parameter, and that again is a placeholder for an actual type. You follow the template prefix by the class, so we have class entity in this example, and then you can use that type parameter t as a placeholder for your member types or your formal parameter types. And so when you go and instantiate that class and specify a type argument, the compiler is going to replace every instance of that t type parameter with the type argument. When you construct an object of type entity, then you can specify int as a type argument, and then the compiler is going to replace every instance of t with that type argument, int for example, in that class definition. As with the function template, the class template is just that, a template. When you actually go and use that struct or class, the compiler will generate the appropriate definition of that class or struct by substituting your type parameters with your type arguments. For this example, I'm using the entity class again, and we use the keyword template to specify to the compiler that this class is a template. It has one type parameter called t, and in the public section we do the constructor, so we have entity. The formal parameter for that is called member p. Just some member parameter, we're going to initialize the member with that. You can see that member variable is in the private section, and that is also of type t. We do the initialization in the initialization list, so we assign member p, the member parameter, to the member variable of this class. Then we have an example of a setter and an example of a getter for that member. So we do void set member. It's going to take in what we want to set that member to. So again, we have a member parameter, and that is also going to be of type t. And in the body of that function, we simply assign member p to member again. Then for the getter, of course, we want to return something. So that is going to get or return a variable of type t. You can see in the body here, we do return member. How do we instantiate that template class? You can see in main, I do entity. I pass in a type argument of int. I have the name for the object that we are constructing, so we do entity1. Again, we are just using some generic class entity for these examples. Okay, so that is entity1, and then we pass in 55 for the construction. To recap, the integer type argument is going to initialize the type parameter. And then the 55 that we pass in right here, that is an actual argument that is going to initialize the formal parameter. That is for the constructor right here. Back in main, I do cout entity1.getMember and build around that, and that works fine. And just to test the setter, we can do entity1.setMember, and I pass in 33 for that. So in other words, the setMember function, the formal parameter for that is going to accept that argument of 33, and in the body we assign that parameter to the member. And following the setter, we simply print it out again using the getMember. Build and run, and that works fine. We get 55 and 33 printed out. Next, I want to talk a bit more about class template member functions. If member functions of a template class are declared in the body of the class, but defined outside of the body, so in other words you separate out the definition and the declaration, then those member functions are defined in a way that is similar to non-member function templates. In other words, similar to global function templates. We have an example of a struct template definition with a member function declaration. We have struct entity, and then in the body we have the declaration, the getMember member function, and that is going to return a type of t. We also have a member of type t in that struct, And then for the definition of that member function, you can see the syntax. We have to do the template prefix, the return type, which in this case is going to be t. As usual, we have to qualify the member function name. We qualify getMember, but the qualification is going to look a bit different. We do entity, which is the struct name, the angle brackets, and then we pass in t's, we pass in that type parameter. Then we have the function body where we return the member. So the syntax is slightly different in that we have the template prefix, and that's similar to non-member function templates, but the qualification is also slightly different from regular member functions in that not only do we provide the template prefix, but we also have that angle brackets following the entity, or in other words following the class or struct name. We have those angle brackets, and then we also pass in the type parameter name, so t in this case. Okay, let's get back to our example. We have the entity class here, and let's say we want to separate out the definition and the declaration of these member functions, so setMember and getMember. We'll start with those, and we'll start with the setMember, so I'll go and make sure I have my prototype, and now we get this function definition for setMember not found. Now let's try and do something I avoid. Entity, the scope resolution operator, and we expect to get the members right, but we don't. Okay, now we provide the template prefix, and again I do the scope resolution operator, and we still do not get the members. Now I provide the angle brackets and I pass in t. Then I do the scope resolution operator, and I can do the setMember. Remember that the setMember function has a formal parameter member p of type t, and we want to assign that to the member. In main, we do the same thing that we've done in the previous subsection, so I'm going to construct entity1, pass in 55 for the constructor, print it out using the getMember function. Then I'm going to use the setMember to set the member of that entity to 33, and then I print it out again. Build and run, and this will work fine. We get 55 and 33. Again, if you remove this here with this qualification and you try and build that, you'll get an error. The use of a class template requires the template argument list. And of course, if you comment out the template prefix, then it's not going to know what t is. So this is our definition for the setMember function. Now let's go and do the getMember function. So we have the prototype or the declaration in the entity class definition in the body of that, and then we do the definition separately outside of the body. Build a run, and this will work fine. And so we've separated out the setMember and the getMember function definitions and declarations. For a quick exercise, separate out the declaration and the definition of the constructor, and then provide a destructor where you also separate out the declaration and the definition. Okay, I'm back in Visual Studio. Let's go and do the constructor first. So I want to separate out the declaration and the definition of the constructor. I'll just copy that. For the constructor, we want to initialize the member to the member parameter. So that is what we are going to do. And back in the body, I want to make sure that I have the declaration right here. So the prototype, end that off with the semicolon. We have all the functionality that we need right here. And that is going to be it for the constructor. Remember that we also have to provide here where we do the qualification. We again have to provide the angle bracket and pass in t as an argument. Next, I'm going to do a destructor. We don't actually need one for this class, but just as a demonstration. And that is a simple example of a destructor definition. We have the declaration in the body right here. And this is the definition of the destructor. Build around that, and that works fine. We get entity constructed, it prints out 55 and 33 as before. We get end of program, and then when program execution reaches the closing curly bracket of the main function, we'll get entity destroyed. Okay, so that means that our destructor works. Class or struct templates can have multiple type parameters, and we have an example of a class template with two different type parameters. Again, we have the template prefix, we do the template keyword, we have the angle brackets, and then we have a list of type parameters. We have T1 for the first type parameter and T2 for the second type parameter. Then we can go and use those type parameters T1 and T2 for member, return, or parameter types. As you can see in this example, we have member1 and member2. Member1 is of type T1, and then member2 is of type T2. So just like function templates can have multiple type parameters, our classes can also have multiple type parameters. And as I mentioned in the videos on the function templates, you can follow your own convention on the type parameter names. Here's a quick example of a struct with two template, or in other words, two type parameters. The struct is called pair, and the type parameters are T1 and T2. We have two members in here. Instead of calling these member1 and member2, I call these first and second. First is of type T1 and second is going to be of type T2. I use first and second for the member names because that is similar to a struct that actually already exists that is provided to us in the standard namespace, and we'll talk about that later. I'll construct a pair, I'll call it pair1, and I'll use the list initialization. Now I can simply do cout to print out first and second, so I do cout pair1.first, cout pair1.second. That'll print out 55 and 8 in this case. A pair struct like this seems very simple, but it's actually very useful, to the point where it's available in the standard namespace and is provided in a utility file. I'll pound include utility, and then I'll actually just go and remove this code that we wrote for the previous example. Now if you don't have the standard namespace included, then you can do std, and then you have pair. Now this starts with a lowercase. We did it in our example with an uppercase, but since we have standard namespace up here, we can just do pair like that. Again, this is similar to what we've done before, and it prints out 8 and 55. The pair struct template also has the swap function. If I Ctrl-Shift spacebar in here, we can see that it takes a reference to a pair that takes in a char and an integer, similar to what we have here. I'll just create another pair, pair2, and I'll change the initialization, so I have b for the char and then 33 for the int, and then I'll pass that in here, pair2. So I'll print out pair1, then I'll do the swap, and then I'll print those out again. And you can see that works. We get 8, 55, and then b and 33. Okay, what I can also do is I can right click on a pair right here and go to the definition, and from this we can see this is a struct where the template prefix, it is in the utility file. If you scroll all the way down, you have the swap right here, you have the two members, first and second. Looking at the implementation may be a bit intimidating, it may be a bit complex, but you don't really have to do that to use it. I'm just showing you that it exists out of interest, and that even for seemingly simple classes there is a lot that you can do. You can do swap, maybe you can overload the assignment operator, and so on. You want to define your class templates in header files. They are typically defined entirely in your .h, or in other words header files, and then included into the source files where you want to actually use those templates. So in other words, if you separate out the definitions and declarations for your member functions of your class or struct templates, then those definitions are going to be in the same header file as the definition of the struct or class.